Welcome to the office. We just learned that we can take a permutation and we can express it as a product of transpositions. There we go, right? We can take any permutation and express it as a collection of transpositions. Cool. The thing is if we write a permutation as a product of transpositions, there's a lot of different ways that we can do that. We expressed that by giving two different presentations in our last example. But what you might notice is that both representations, right, we rewrote it as transpositions. Both of them had the same number of transpositions. So if you look back at your notes, you'll notice that it was 4 transpositions that gave us that representation of the permutation. So the question is will it always be 4? Yes, right? For that example, it will always be 4. No matter how we rewrite it as transpositions, it should always be 4. Now, what is it in general? In general, if we have a permutation, it can be expressed as specifically one collection of permutations. Now, you know what? Maybe let's say Dr. Reinhardt is alive. It's not always going to be 4. Okay. You know what? You could take that thing, you could transpose something, and then you could undo that transposition. So you could add 2 more. So you could transpose, and then undo the transposition. So you could take that 4 and turn it into 6. Okay. I'm not going to argue that. You're right. But what you cannot do is you can't transpose, and then do just 1 more to fix those 2. You always have to add them in pairs. Do it, so you have your desired collection of transpositions. If you wanted to come up with some other collection, you can add more, or you could find a different representation. But the point is that it's always going to be either an even number or an odd number of transpositions. Always going to be an even number or an odd number of transpositions. You cannot find different representations that give a different parity, even versus odd. So that's awesome. That means that our permutations themselves we can describe as being even or odd, and that's our theorem and definition that we would like to share from this video. So no permutation can be expressed both as a product of an even number of transpositions and as an odd number of transpositions. That's what we just talked about. Excellent. So there's either an even number or an odd number. Therefore, we can give a definition. Our permutation is even or odd according to whether it has an even or odd number of transpositions. Awesome. Fantastic. So then we just want to consider a brief example. Is this permutation even or is it odd? Simple enough. If we use the presentation that the book gave for finding a way to represent it as products of transpositions, we first recognize that 1,4 is already a transposition. I'm not even worried about what these things say. They may not be disjoint. They might be disjoint. They don't have to be. We should be all set to be able to say, all right, here we are. What is it? Just take each of these cycles, disjoint or not, and rewrite them as a product of transpositions. So the book says that 3, 10, 7 should be written as 3, 7 and 3, 10. And then 5, 9, 6, 8 should be written as 5, 8, 5, 6, 5, 9. That is 3 goes to 7, then 3 goes to 10. 5 goes to 8, 5 goes to 6, 5 goes to 9. That's what I've done there. So there's 1, 2, 3, 4, 5, 6 transpositions. 6, of course, is an even number. So tau here is an even permutation. Excellent. Double check that. That stayed the same. 3 to 7, 3 to 10. 5 to 9, 5 to 6, 5 to 8, 1, 2, 3, 4, 5, 6. Make sure I didn't do something silly in my counting. All right, excellent. So tau is an even permutation. We're all set. That's all that they were looking for there. So thank you for your time and your attention. I'll see you guys later back here in the office.